name is Selin ALTUN. I'm a student at the Department of Electrical and Electronics Engineering at Bilkent University. In this video, I'll be presenting my Physics 102 project, which is about investigation of settling behavior in RC circuits. First, I should explain RC circuits. RC circuits consist of resistors and capacitors. Resistors are in charge of controlling the current flow, while capacitors store electric energy. RC circuits can be built in parallel and in series, although in this experiment I will be using the series configuration. One key feature of RC circuits is the time delay that they experience when voltage is applied. This time delay mainly depends on the reactive components connected to the circuit. This time delay is defined as the time constant, symbolized by this tau, and can be calculated using this formula. When a step input is applied to an RC circuit, the capacitor doesn't charge instantly. Instead, the output voltage increases gradually, reaching around 63% of its final value after one time constant has passed. Now, when an AC signal is applied, the frequency response of the circuit changes. At low frequencies, the output follows the input. At high frequencies, the output drops. The cutoff frequency, where the output reaches half its maximum, is given by this formula. In short, RC circuits help us understand how circuits respond to time and frequency. And in this experiment, we will visualize this on an oscilloscope. For the setup of this experiment, I built a simple RC circuit on a breadboard where the capacitor and the resistor are connected in series. The capacitor will have a constant capacitance of 10 microfarad, and I will connect 3 resistors with varying resistance one by one to the circuit. The circuit is connected to a signal generator which generates a square signal with appropriate frequency and 5-volt peak-to-peak value. Then I will connect the oscilloscope probe in between the resistor and the capacitor to view the results on the oscilloscope screen. As you can see from this demonstration, with this setup we can view the capacitor's charging and discharging waveform on the oscilloscope screen. By using the cursors on the oscilloscope, I can precisely determine the measured value of the time constant. First, I made predictions of the time constant for all 3 circuits by using the theoretical equation in question. To check the accuracy of my predictions, I repeated the process of connecting the oscilloscope probe between the capacitor and the resistor for each circuit with resistors of varying resistance. For each case, I measured the time it takes for the capacitor to charge to approximately 63% of its final value using the oscilloscope's cursor function. By comparing the theoretical time constant and the measured time constant, the average error can be calculated to be overall 5.32%. This experiment effectively demonstrated the behavior of an RC circuit. The waveforms on the oscilloscope match the expected exponential charging behavior and show how resistance affects charging rate. The measured and calculated value of the time constant show that it's directly proportional to the resistance, and the slope of the graph relating these terms is about 10 microfarad, matching the capacitance. The average error was found to be only 5.32%, confirming the experiment's reliability. Several factors may have contributed to this error, the main one being the component tolerances of the resistors and the capacitor, which can commonly reach up to 5%, similar to the error found in this experiment. Other reasons for error could have been limitations in the oscilloscope cursors in determining the duration of the charging and the unintended capacitance from the breadboard, jumper cables, and oscilloscope probe. Finally, electrical noise coming from the signal generator might have impacted the results as well.